Hello students, welcome to the lecture 7. Today is March 24th, and in this lecture we're going to talk about second derivative test, and this is a test to classify critical points. So that's our first rule for today, and this theorem tells us the following. So it's a second derivative test, and to find local max and local mean. All right, so let f of x be twice differentiable function on an open interval, let's say AB, which contains x sub 0 or x equal to x sub 0. Let x equal to x sub 0 be a critical point of f of x such that f prime at x sub 0 is equal to 0. So those points we call stationary critical point. All right, then the outcome says the following. And what is the idea of the outcome? If you have a function that has a horizontal tangent line, that's what this part says, then if the function is concave up, like over here, concave up, right? So concave up. Then we have a local mean. And if the function is concave down, we have a local max. All right, that's what we want to write down. So first part says if f double prime at x sub 0 is positive, right? And this is the situation that we have. The function looks like this. Then f of x has a local maximum at x equal to x sub 0. So we described this situation. Now we have to describe the other one. If f double prime at x sub 0 is less than 0, so the function looks like this, and we're on the top, then f of x has a local minimum messed it up. So this one should say local minimum. Didn't do it right? We're on the bottom. So minimum, and this one should be on the top, which is local maximum. All right, so that's good that I saw the mistake. And at x equal to x sub 0. Unfortunately, in this theorem, there is a third part which I haven't discussed yet, but let's look what this third part is. What if f double prime at x sub 0 is equal to 0? Unfortunately, no conclusion can be made, right? So basically, we have to use first derivative test. So why do you think we have then second derivative test? Because this test is much faster than the first derivative test. You just calculate second derivative, you plug in the critical point into it, and you get the answer right away. Unfortunately, sometimes it's inconclusive. All right, so let's look at some examples. And the first example we're gonna do is this example. F of x is equal to 2x cubed minus 6x squared plus 5. The assignment asks us to find critical points, and classify them. All right, when it says classify them, tell whether it's local max, local mean, or neither of those. Sometimes people just say classify. So we're going to use second derivative test. Now you have a choice. When it doesn't specify, when the assignment doesn't specify how to deal with it, you can choose. But since we're practicing with the second derivative test, that's what we're going to do. All right, so second derivative test. So for this, we need second derivative. So let's start. We do the first derivative, and it's derivative of 2x cubed minus 6x squared plus 5. So we get 2 times 3, which is 6, and we decrease the power by 1, so we get 6x squared. 6 times 2 is 12, so we're going to get negative 12x. And derivative of 5 is 0. But after that, we don't do the sign graph. We just, oh no, we need to do the sign graph. Maybe not. We just need to find critical points. All right, so we take 6x squared minus 12x, we set it equal to 0 to find critical points. So we factor out 6x, we're left with 6x, x minus 2 equals to 0, so x is equal to 0, or x minus 2 is equal to 0, since 6 cannot be equal to 0. So we have two solutions. One is x equals 0 and x equals 2. So this is our critical points, and these critical points make our first derivative equal to 0. So we can apply second derivative test. Just to remind you, if you go back to the derivative, it says that first derivative at the critical point has to be equal to 0. If first derivative at critical point is undefined, we cannot use second derivative test. All right, so we reviewed this. So now we calculate second derivative. So we get derivative of 6x squared minus 12x. All right, so we get 6 times 2, which is 12x minus 12. And this is our second derivative. Now we have to take x equals 0 and plug it into the second derivative. So we're going to get 12 times 0 minus 12, which is negative 12, which is less than 0. So our function is concave down, and our point is on the top. So conclusion, f of x has a local maximum at x equal to 0. Again, we didn't really provide the point of local maximum, because to provide the point, we also need to find the y value. We only found the x value, but that's good enough. Unless assignment specifically asks us to find the y value, we wouldn't do that. So now we're going to take x equals 2, and we're going to do the same. We're going to plug it into the second derivative. So 12 times 2 minus 12, so we're going to get 24 minus 12, which is 12, which is positive. So our function is concave up, and we are on the bottom. Since we're on the bottom, conclusion, f of x has a local minimum at x equals 2. And we classified our critical points, so we are done with this exercise. All right, so another example is the following. So in this example, we're going to deal with the following function. F of x is 3x to the 4 minus 4x cubed plus minus 2. All right, so again, the assignment is the same. Find critical points and classify them. All right, so again, we're going to start with the derivative to find critical points. So we calculate f prime. So 3x to the 4 gives us 12x cubed minus 4 times 3 is 12x squared, and derivative of negative 2 is 0. So we set it equal to 0. We take 12x squared out, and we're left with this product, 12x squared x minus 1. So it's either x squared equal to 0 or x minus 1 equal to 0. So this gives us x equals 0 if we take a square root on both sides, and this one gives us 1. So we have two critical points. They both make derivative equal to 0. That allows us to apply second derivative test. So, so we want to apply second derivative test. So in order to do that, we're going to calculate second derivative, which is the derivative of 12x cubed minus 12x squared. 12 times 3 is, and we're calculating derivative. So 12 times 3 is 36x squared, and 12 times 2 is 24x. So now we're going to take x equals 0, and we're going to plug it into the second derivative. So we're going to get second derivative evaluated at 0. So it's 36 times 0 squared minus 24 times 0. And if we calculate it, we're going to get 0, and we're going to get 0. So the answer is 0. So no conclusion can be made according to the second derivative test. No conclusion. So for this x equals 0, we would have to use the first derivative test. We will use first derivative test. Later, right? Later. First, before we do that, we're going to do the second critical point, x equals 1. So we're going to take x equals 1. This is our second critical point, and we're going to plug it into the second derivative. So it's going to be 12 times, sorry, not 12, but 36 times 1 squared minus 24 times 1. So it's 36 minus 24, which is 12, which is positive. So we have a point on the bottom, so it's a local minimum. So we say f of x has a local minimum at x equals 1. Now we have to reconsider x equals 0. So for x equals 0, this is our 0, this is our 1. We already know what's going on at 1, right? We just have to figure out what's going on in 0. But when we do the sine graph for the first derivative, we cannot go beyond 1. We just have to be in this region on the left side of 0, then on the right side of 0, but not beyond 1. And then we take testing point over here, which is -1. So we're going to calculate first derivative at -1. And our first derivative was 12x cubed minus 12x squared. So 12 negative 1 cubed minus 12 times negative 1 squared. All right, so let's try to calculate. This part is positive, this part is negative, so we have negative 12 minus 12, so it's negative 24, so it's less than 0. So we put a big minus. Then we need to take a testing point between 0 and 1. Let's take 1/2, right? Let's take 1/2. All right, so we need to calculate f prime of 1/2. So it's going to be 12 times 1/2 cubed minus 12 times 1/2 squared. So let's try to do that. 1/2 cubed is 8, so it's 12 over 8 minus, and 1/2 squared is 1/4. All right, so let's try to calculate it. This one we can simplify, so it's 3 over 2, or 1.5, minus 12 over 4 is 3, so we're going to get negative 1.5. And you can use a small calculator to do these calculations. You don't have to do them in your head. And we got minus and minus. What can we say about the critical point when the first derivative does not change its sign? Or it's neither local max, nor local mean. Right? It's neither of those. And the last thing we can do is to plot this function to be sure that we did it right. So our function was 3x to the 4, right? 3x to the 4 minus 4x cubed minus 2. So we go to plots, we type 3 times x to the 4 minus 4 times x cubed minus 2. All right, and I'll probably decrease these values. We want negative 1 and 2. All right, so let's look at this function over here. All right, maybe we should zoom in a little bit on 0. Zoom in a little bit on 0 to make a good understanding on what's going on. So I'll change my interval to negative 0.5 to 1.5, so make it a little bit smaller. All right, so it's easier to see what's going on. So we take this, we put it back, we decrease the size, and we look at this picture. So what can we say from this picture? We can clearly see this is our local mean. We figured it out correctly. What's going on at 0? At 0, we have a change of concavity, right? But it's not local max or local mean. Just the concavity changes, and we have a horizontal tangent line. And that concludes this small lecture where we learned the second derivative test to figure out local max and local mean. And I'll see you in the next lecture.